In metalworking, rolling is a metal forming process in which metal stock is passed through one or more pairs of rolls to reduce the thickness and to make the thickness uniform. The concept is similar to the rolling of dough. Rolling is classified according to the temperature of the metal rolled. If the temperature of the metal is above its recrystallization temperature, then the process is known as hot rolling. If the temperature of the metal is below its recrystallization temperature, the process is known as cold rolling. In terms of usage, hot rolling process is more tonnage than any other manufacturing process, and cold rolling process is the most tonnage out of all cold working processes. Roll stands holding pairs of rolls are grouped together into rolling mills that can quickly process metal, typically steel, into products such as structural steel, bar stock, and rails. Most steel mills have rolling mill divisions that convert the semi-finished casting products into finished products. There are many types of rolling processes, including ring rolling, roll bending, roll forming, profile rolling, and controlled rolling. History: iron and steel. The discovery of the rolling mill in Europe may be attributed to Leonardo da Vinci and his drawings. The earliest rolling mills in crude form, but the same basic principles were found in Middle East and South Asia as early as 600 BCE. Earliest rolling mills were slitting mills, which were introduced from what is now Belgium to England in 1590. These passed flat bars between rolls to form a plate of iron, which was then passed between grooved rolls to produce rods of iron. The first experiments at rolling iron for tin plate took place about 1670. In 1697, Major John Hanbury erected a mill at Pontypool to roll Pontypool plates, black plate. Later this began to be re-rolled on tin to make tin plate. The earlier production of plate iron in Europe had been in forges, not rolling mills. The slitting mill was adapted to producing hoops and iron with a half-round or other sections by means that were the subject of two patents of c. 1679. Some of the earliest literature on rolling mills can be traced back to Christopher Polhem in 1761 in Patriotiste Testamente, where he mentions rolling mills for both plate and bar iron. He also explains how rolling mills can save on time and labor because a rolling mill can produce 10 to 20 or more bars at the same time. A patent was granted to Thomas Blockley of England in 1759 for the polishing and rolling of metals. Another patent was granted in 1766 to Richard Ford of England for the first tandem mill. A tandem mill is one in which the metal is rolled in successive stands. Ford's tandem mill was for hot rolling of wire rods. Other metals rolling mills for lead seem to have existed by the late 17th century. Copper and brass were also rolled by the late 18th century. Modern rolling practice can be attributed to the pioneering efforts of Henry Court of Funtley Iron Mills, near Fareham, England. In 1783 a patent was issued to Henry Court for his use of grooved rolls for rolling iron bars. With this new design, mills were able to produce 15 times more output per day than with a hammer. Although Court was not the first to use grooved rolls, he was first to combine the use of many of the best features of various iron-making and shaping processes known at the time. Thus modern writers have called him father of modern rolling. The first rail rolling mill was established by John Birkinshaw in 1820, where he produced fish-bellied wrought iron rails in lengths of 15 to 18 feet. With the advancement of technology in rolling mills, the size of rolling mills grew rapidly along with the size products being rolled. Example of this was at the Great Exhibition in 1851. A plate 20 feet long, 3.5 feet wide, and 7/16 of inch thick, weighed 1,125 pounds was exhibited exhibited by the Concert Iron Company. Further evolution of the rolling mill came with the introduction of 3 high mills in 1853 used for rolling heavy sections. Hot and cold rolling. Hot rolling is a metalworking process that occurs above the recrystallization temperature of the material. After the grains deform during processing, they recrystallize, which maintains an equiaxed microstructure and prevents the metal from work hardening. The starting material is usually large pieces of metal, like semi-finished casting products, such as slabs, blooms, and billets. If these products came from a continuous casting operation, the products are usually fed directly into the rolling mills at the proper temperature. In smaller operations, the material starts at room temperature and must be heated. This is done in a gas or oil-fired soaking pit for larger workpieces, and for smaller workpieces induction heating is used. As the material is worked, the temperature must be monitored to make sure it remains above the recrystallization temperature. To maintain a safety factor, a finishing temperature is defined above the recrystallization temperature. This is usually 50 to 100 degrees Celsius above the recrystallization temperature. If the temperature does drop below this temperature, the material must be reheated before more hot rolling. Hot rolled metals generally have little directionality in the mechanical properties and deformation-induced residual stresses. However, in certain instances, non-metallic inclusions will impart some directionality, and workpieces less than 20 mm thick often have some directional properties. Also, non-uniform cooling will induce a lot of residual stresses, which usually occurs in shapes that have a non-uniform cross-section, such as I-beams. While the finished product is of good quality, the surface is covered in mill scale, which is an oxide that forms at high temperatures. It is usually removed via pickling at the smooth clean surface process, which reveals a smooth surface. Dimensional tolerances are usually 2 to 5% of the overall dimension. Hot-rolled mild steel seems to have a wider tolerance for amount of included carbon than does cold-rolled steel, and is therefore more difficult for a blacksmith to use. Also, for similar metals, hot-rolled products seem to be less costly than cold-rolled ones. Hot rolling is used mainly to produce sheet metal or simple cross-sections, such as rail tracks. Other typical uses for hot-rolled metal includes truck frames, automotive wheels, pipe and tubular, water heaters, agriculture equipment, strappings, stampings, compressor shells, railcar components, wheel rims, metal buildings, railroad hopper cars, doors, shelving, discs, guardrails, automotive clutch plates. Shape rolling design. Rolling mills are often divided into roughing, intermediate and finishing rolling cages. During shape rolling, an initial billet with edge of diameter typically ranging between 100 to 140 mm is continuously deformed to produce a certain finished product with smaller cross-section dimension and geometry. Different sequences can be adopted to produce a certain final product starting from a given billet. However, since each rolling mill is significantly expensive, a typical requirement is to contract the number of rolling passes. Different approaches have been achieved, including empirical knowledge, employment of numerical models, and artificial intelligence techniques. Lamb-et al. Validated a finite element model for predicting the final shape of a rolled bar in round flat pass. One of the major concerns when designing rolling mills is to reduce the number of passes. A possible solution to such requirement is represented by the slit pass, also called split pass, which divided an incoming bar into a more subpart, thus virtually increasing the cross-section reduction ratio per pass as reported by Lamb-et. Another solution for reducing the number of passes in the rolling mills is the employment of automated systems for roll pass design as that proposed by Lamb-et in Langella. Subsequently, Lam-BRC further developed an automated system based on artificial intelligence and particularly an integrated system including an inferential engine based on genetic algorithms, a knowledge database based on an artificial neural network trained by a parametric finite element model, and to optimize and automatically design rolling mills. Cold rolling occurs with the metal below its recrystallization temperature, which increases the strength via strain hardening up to 20%. It also improved the surface finish and holds tighter tolerances. Commonly cold-rolled products include sheets, strips, bars, and rods. These products are usually smaller than the same products that are hot-rolled. Because of the smaller size of the workpieces and the greater strength, as compared to hot-rolled stock, for higher cluster mills are used. Cold rolling cannot reduce the thickness of a workpiece as much as hot rolling in a single pass. Cold-rolled sheets and strips come in various conditions: full hard, half hard, quarter hard, and skin roll. Full hard rolling reduces the thickness by 50%, while the others involve less of a reduction. Skin rolling, also known as a skin pass, involves the least amount of reduction, 0.5 to 1%. It is used to produce a smooth surface, a uniform thickness, and reduce the yield point phenomenon. It locks dislocations at the surface and thereby reduces the possibility of formation of Luders bands. To avoid the formation of Luders bands, it is necessary to create substantial density of unpinned dislocations in ferrite matrix. It is also used to break up the spangles in galvanized steel. Skin-rolled stock is usually used in subsequent cold working processes where good ductility is required. Other shapes can be cold rolled if the cross-section is relatively uniform and the transverse dimension is relatively small. Cold rolling shapes requires a series of shaping operations, usually along the lines of sizing, breakdown, roughing, semi-roughing, semi-finishing, and finishing. If processed by a blacksmith, the smoother, more consistent, and lower levels of carbon encapsulated in the steel makes it easier to process, but at the cost of being more expensive. Typical uses for cold-rolled steel include metal furniture, desks, filing cabinets, tables, chairs, motorcycle exhaust pipes, computer cabinets and hardware, home appliances and components, shelving, lighting fixtures, hinges, tubing, steel drums, lawn mowers, electronic cabinetry, water heaters, metal containers, and a variety of construction-related products. Processes. Roll bending produces a cylindrical shaped product from plated steel metals. Roll forming. Roll bending. A plate rolling is a continuous bending operation in which a long strip of metal is passed through consecutive sets of rolls, or stands, each performing only an incremental part of the bend, until the desired cross-section profile is obtained. Roll forming is ideal for producing parts with long lengths or in large quantities. There are three main processes: 4 rollers, 3 rollers and 2 rollers, each of which has different advantages according to the desired specifications of the output plate. Flat rolling. Flat rolling is the most basic form of rolling, with the starting and ending material having a rectangular cross-section. The material is fed in between 2 rollers, called working rolls, that rotate in opposite directions. The gap between the 2 rolls is less than the thickness of the starting material, which causes it to deform. The decrease in material thickness causes the material to elongate. The friction at the interface between the material and the rolls causes the material to be pushed through. The amount of deformation possible in a single pass is limited by the friction between the rolls. If the change in thickness is too great, the rolls just slip over the material and do not draw it in. The final product is either sheet or plate, with the former being less than 6 mm thick and the latter greater than. However, heavy plates tend to be formed using a press which is termed forming, rather than rolling. Often the rolls are heated to assist in the workability of the metal. Lubrication is often used to keep the workpiece from sticking to the rolls. To fine-tune the process, the speed of the rolls and the temperature of the rollers are adjusted. H is sheet metal with a thickness less than 200 micrometers. The rolling is done in a cluster mill because the small thickness requires a small diameter rolls. To reduce the need for small rolls, back rolling is used, which rolls multiple sheets together to increase the effective starting thickness. As the foil sheets come through the rollers, they are trimmed and slitted with circular razor-like knives. Trimming refers to the edges of the foil, while slitting involves cutting it into several sheets. Aluminum foil is the most commonly produced product for back rolling. This is evident from the two different surface finishes. The shiny side is on the roll side and the dull side is against the other sheet of foil. Ring rolling. Ring rolling is a specialized type of hot rolling that increases the diameter of a ring. The starting material is a thick-walled ring. This workpiece is placed between two rolls, an inner idler roll and a driven roll, which presses the ring from the outside. As the rolling occurs, the wall thickness decreases as the diameter increases. The rolls may be shaped to form various cross-sectional shapes. The resulting grain structure is circumferential, which gives better mechanical properties. Diameters can be as large as 8 meters and face heights as tall as 2 meters. Common applications include bearings, gears, rockets, turbines, airplanes, pipes, and pressure vessels. Structural shape rolling. Controlled rolling. Controlled rolling is a type of thermomechanical processing which integrates controlled deformation and heat treating. The heat which brings the workpiece above the recrystallization temperature is also used to perform the heat treatments so that any subsequent heat treating is unnecessary. Types of heat treatments include the production of a fine grain structure, controlling the nature, size, and distribution of various transformation products, inducing precipitation, hardening, and controlling the toughness. In order to achieve this, the entire process must be closely monitored and controlled. Common variables in controlled rolling include the starting material composition and structure, deformation levels, temperatures at various stages, and cool-down conditions. The benefits of controlled rolling include better mechanical properties and energy savings. Forge rolling. Forge rolling is a longitudinal rolling process to reduce the cross-sectional area of heated bars or billets by leading them between two contrary, rotating roll segments. The process is mainly used to provide optimized material distribution for subsequent die forging processes. Owing to this, a better material utilization, lower process forces and better surface quality of parts can be achieved in die forging processes. Basically, any forgeable metal can also be forge rolled. Forge rolling is mainly used to pry from long-scaled billets through a targeted mass distribution for parts such as crankshafts, P-connection rods, steering knuckles and vehicle axles. Narrowest manufacturing tolerances can only partially be achieved by forge rolling. This is the main reason why forge rolling is rarely used for finishing, but mainly for preforming. Characteristics of forge rolling: high productivity and high material utilization. Good surface quality of forge-rolled workpieces. Extended tool lifetime. Small tools and low tool costs. Improved mechanical properties due to optimized grain flow compared to exclusively die-forged workpieces. Mills. A rolling mill, also known as the reduction mill or mill, has a common construction independent of the specific type of rolling being performed. Work rolls. Backup rolls are intended to provide rigid support required by the working rolls to prevent bending under the rolling load. Rolling balance system to ensure that the upper work and backup rolls are maintained in proper position relative to lower rolls. Roll changing devices. Use of an overhead crane and a unit designed to attach to the neck of the roll to be removed from or inserted into the mill. Mill protection devices. To ensure that forces applied to the backup roll chocks are not of such a magnitude to fracture the roll necks or damage the mill housing. Roll cooling and lubrication systems. Pinions, gears to divide power between the two spindles, rotating them at the same speed but in different directions. Gearing, to establish desired rolling speed. Drive motors, rolling narrow foil product to thousands of horsepower. Electrical controls, constant and variable voltages applied to the motors. Coilers and uncoilers, to unroll and roll up coils of metal. Slabs of the feed material for hot strip mills or plate mills and blooms are rolled to billets in a billet mill or large sections in a structural mill. The output from a strip mill is coiled and, subsequently, used as the feed for a cold rolling mill used directly by fabricators. Billets for re-rolling are subsequently rolled in either a merchant bar or rod mill. Merchant bar mills produce a variety of shaped products such as angles, channels, beams, rounds and hexagons. Configurations mills are designed in different types of configurations, with the most basic being a two-high non-reversing, which means there are two rolls that only turn in one direction. The two-high reversing mill has rolls that can rotate in both directions, but the disadvantage is that the rolls must be stopped, reversed, and then brought back up to rolling speed between each pass. To resolve this, the three-high mill was invented, which uses three rolls that rotate in one direction. The metal is fed through two of the rolls and then returned through the other pair. The disadvantage to this system is the workpiece must be lifted and lowered using an elevator. All of these mills are usually used for primary rolling and the roll diameters range from 60 to 140 centimeters. To minimize the roll diameter, a 4-high cluster mill is used. A small roll diameter is advantageous because less roll is in contact with the material, which results in a lower force and power requirement. The problem with a small roll is a reduction of stiffness, which is overcome using backup rolls. These backup rolls are larger and contact the backside of the smaller rolls. A 4-high mill has 4 rolls, 2 small and 2 large. A cluster mill has more than 4 rolls, usually in 3 tiers. These types of mills are commonly used to hot roll wide plates, most cold rolling applications, and to roll foils. Historically, mills were classified by the product produced, blooming, cogging and slabbing mills being the preparatory mills to rolling finished rails, shapes or plates, respectively. If reversing, they are from 34 to 48 inches in diameter, and if 3-high, from 28 to 42 inches in diameter. Billet mills, 3-high, rolls from 24 to 32 inches in diameter, used for the further reduction of blooms down to 1.5 x 1.5-inch billets, being the preparatory mills for the bar and rod. Beam mills, 3-high, rolls from 28 to 36 inches in diameter, for the production of heavy beams and channels 12 inches and over. Rail mills with rolls from 26 to 40 inches in diameter. Shape mills with rolls from 20 to 26 inches in diameter, for smaller sizes of beams and channels and other structural shapes. Merchant bar mills with rolls from 16 to 20 inches inches in diameter. Small merchant bar mills with finishing rolls from 8 to 16 inches in diameter generally arranged with a larger size roughing stand. Rod and wire mills with finishing rolls from 8 to 12 inches in diameter, always arranged with larger size roughing stands. Hoop and cotton tie mills, similar to small merchant bar mills. Armor plate mills with rolls from 44 to 50 inches in diameter and 140 to 180 inch body. Plate mills with rolls from 28 to 44 inches in diameter. Sheet mills with rolls from 20 to 32 inches in diameter. Universal mills for the production of square-edged are called universal plates and various wide-flanged shapes by a system of vertical and horizontal rolls. Tandem Mill. A tandem mill is a special type of modern rolling mill where rolling is done in one pass. In a traditional rolling mill, rolling is done in several passes. But in tandem mill there are several stands and reductions take place successively. The number of stands ranges from 2 to 18. Tandem mills can be either of hot to cold rolling mill types.